Katrina here. Today we're going to dive into linear algebra and talk about matrix determinants. Make sure to watch end so that you see all the examples for 2x2 and 3x3 matrices. And please subscribe for more videos. Okay, let's start by looking at what the definition is for a determinant. So very simply put, a determinant is a scalar value that provides key insights into matrices. So we denote determinants as det, so D-E-T, and then in brackets A, for some matrix A. So it can tell us about the invertibility of the matrix. It can tell us whether the matrix has unique solutions, and it can also give us key insights about whether volume is preserved when we transform our matrix into space. So for today's lesson, I'm going to show you how to calculate the determinant for 2x2 matrices and 3x3 matrices. And then this understanding and these learnings can be then applied to larger matrices as well. So first of all, let's look into the conditions, because not all matrices are convertible. So the first condition that we have to consider, and it's the most important one, is that our matrix must be square. So a square matrix means that the number of rows has to equal to the number of columns. So we usually write this as an n by n matrix. So number of rows has to equal the number of columns. Okay, so now that's like the main condition that we have to meet. And the next things I'm going to tell you are kind of important qualities of a matrix that we should look out for. So the next thing is whether the determinant is 0 or not. So let's consider, again, some matrix A. So we're taking the determinant of A. If our determinant equals to 0, what that tells us is that our matrix is singular. And you might be wondering, what does it mean to have a singular matrix? If you have a singular matrix, that means that the matrix does not have an inverse, so not invertible. And I think I spelled that wrong, invertible. There we go. So it's not invertible, and then in addition, it also could mean that the systems of equations that it represents may not have a unique solution. So may not have a unique solution. So when we're doing linear algebra, those are two big things that we often want to determine, is whether our matrix is singular or not. Because if it's singular, then it's not invertible, and it also may not have a unique solution. Okay, so we said that's what happens if our determinant equals to 0. Now, what if our determinant does not equal to 0? What do we know about our matrix then? Well, if it doesn't equal to 0, that means that the matrix is in fact invertible. And since it's invertible, we also see that it has full rank. So those are two key things that we want to know. Oops, so if it's not 0. So now we know about the conditions, and we have a bit of an idea of properties of our matrix, whether if our determinant equals to 0 or if it doesn't equal to 0. So next step is I'm going to show you how we can actually calculate the determinant. So we're going to start off with a 2x2 case. So we're going to say that we have some matrix A, and it equals to this 2x2 matrix, and each entry is the following. So we have A, B, C, D. So this is a 2x2 matrix. And now we want to calculate the determinant of A. So for a 2x2 matrix, it's a simple case, because what we have to do is simply take our A and D values and then subtract our C and B values. So our equation just becomes AD minus BC. So remember that our determinant gives us a scalar value. So this is a scalar output. So we have our matrices, we have our vectors. These are vectors, obviously, but then the determinant gives us a scalar output. So let's go ahead and dive into one example so that you can see this in action. So let's consider some matrix A, which has the entries 3, 5, 2, and 4. And now we want to calculate the determinant. So we set this up as the determinant of A equals to AD minus BC, right? So if we just get the numbers from our matrix, we get that we have 3 times 4 minus 2 times 5. So if we simplify this, we get 12 minus 10, and this equals to 2. So now let's take a second and analyze what does this 2 mean. So obviously 2 does not equal to 0. So that means that the matrix is not singular. So if it's not singular, that means that it is invertible. So that is great to learn that information about our matrix because that has further implications in linear algebra. So this is invertible. That means we can manipulate it, we can take its inverse, and ultimately this means that we can decompose this matrix using other techniques that I will show you in my later videos. Okay, let's take a look at another example. So we'll do our second example for 2 by 2 matrices. This time let's consider some matrix B that has the entries 1, 2, 2, and 4. So we can obviously see that it's 2 by 2, so this is a square matrix because the number of rows, so this is our number of rows here, equals to our number of columns. So right away we see that we meet our condition so that we can go ahead and take the determinant. So the determinant of B, this equals to, again, AD minus BC. I always encourage you to write out the equation first so that you can just input your values and you can go ahead. So that means we've got 1 times 4 minus 2 times 2. This equals to 4 minus 4, which equals to 0. Okay, so now that we have the determinant of B equals to 0, so that means that it is in fact singular. So if it's singular, then we have that it is non-invertible. So we can see we used the same strategy for both of these examples, and we were able to determine then whether these matrices were singular or not, which corresponds to whether they are invertible or not. Great. So now we're going to enter the realm of 3 by 3 matrices. So we just have to use the skills that we learned for our 2 by 2 matrices, and now we have to expand them into a bigger dimension. So with this, we're going to consider some matrix C, and this is going to be a 3 by 3 matrix. So let's have the entries A, B, C, D, E, F, and then we have G, H, I. So we have to use something called Laplace expansion. So we're going to write that out over here. So we have Laplace expansion. So the Laplace expansion helps us determine what the determinant is for matrices that are larger than 2 by 2. So it has this special matrix over here that helps us determine whether our coefficients are going to be positive or negative. So it goes plus, minus, plus, and then we alternate every time. So if you have some entry over here, it's going to have a positive coefficient, whereas if you have an entry starting here, it will have a negative coefficient, and so on. So essentially what we have to do is that we have to go down either one row or one column of this matrix and then calculate each minor determinant. So I'm going to show you what that looks like. So say, for example, that we're going to go down this first row. So we're going to go down row 1 of our 3 by 3 matrix. Just so you know, you can either choose to go down a row or a column. We're going to choose the row for this example. So now that you know that, I'm going to show you how this works. So since we've decided to go down the row, we're going to start with our value A. So we're going to write out determinant of matrix C. So we're going to go step by step through this process. So since we're going down row A, we're going to start by looking at A. We can see that from our Laplace expansion, we are going to have a positive leading coefficient. So we can go ahead and write A, and we can keep it as positive. Then what we do from there is the row and column adjacent to A, you're going to block out. So let's just put a different color. We're going to block this out. And then what's going to happen is that I want you to then consider the matrix, submatrix or minor matrix that we have left. So once we have A as our anchor point, we block out the row and column adjacent to it, and then we're looking at this minor matrix. So then what we do is we have to multiply A by the determinant of this minor matrix. So the determinant of E, F, H, I. And just so you know, these straight lines here, they represent, that's another way to represent the determinant. Okay, so now let's go ahead and do this for the next entry. So we said we're going along row 1. So now we're going to look at the second entry, which is B. So if we look at our Laplace expansion, we see that this must have a negative coefficient. So now we write minus B. And we're going to do the same thing, is we're going to look at what is the row and column kind of adjacent to B. So that would be this row over here and then this column over here. So that means we have D, G, F, and I left for our minor matrix. So we have B multiplied by the determinant of D, F, G, and I. Okay? So now we're going to repeat this process once more in order to find our last term. So since we're moving along the row, we're now going to look at our final value in the row, which is C, and this has a positive value in the Laplace expansion. So that means we're going to have plus C. And again, we're going to cancel out the rows and columns adjacent to C, and we're going to look at what minor matrix do we have left. So our minor matrix that we have left is matrix D, E, G, and H. And that's it. So we've gone through our whole row, our first row, and we've used the Laplace expansion, and by doing that, we have derived the formula for our determinant of C. So now for each submatrix or each minor matrix that we have over here, so you've got 3 of them, since these are all 2 by 2 matrices, we can then use the AD minus BC rule in order to find those determinants. And then this basically reduces a more challenging 3 by 3 dimensional problem into a series of 2 by 2 matrices, which we already know how to deal with. So let's do an example so that we can see this formula in action. So for example, we have our matrix C, and it has the following entries: 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're just taking our integers from 1 to 9. And now let's go ahead and use our formula, which we work so hard to derive up here. So that means that our matrix C equals to our first entry here, which is R1. So we've got 1 multiplied by the determinant of our minor matrix here. So we've got 5, 6, 8, 9. And now let's go ahead to do that for our next entry. So we are looking at 2. And remember from our Laplace expansion that that has to be negative over there. So we do minus 2 multiplied by our next minor matrix, which is going to be 4, 6, 7, and 9. And then lastly, let's go to our last value, which is our 3. And from Laplace expansion, we have that it is positive. And then our minor matrix here is this guy over there. So we've got 4, 5, 7, and 8. And now we just have to use our AD minus BC rule to find all our minor determinants. Okay, so we have 1 multiplied by 5 times 9 minus 6 times 8. That's our first term. And then we can just calculate this one first. So this equals to 45 minus 48, which equals to negative 3. So let's just label these as 1, 2, and 3, and we'll calculate these individually. So we have our answer for 1. Now let's go ahead to find our answer for 2. So this equals to, let's see what we've got over here, negative 2 times 4 times 9 minus 6 times 7. And this equals to negative 2 times 36 minus 42, which equals to negative 2 times negative 6, which equals to positive 12. Okay, and now we're going to go ahead and do that for our last one, for number 3. So from our third one here, let's see what we've got. We've got 3 times 4 times 8 minus 5 times 7. Okay, so then that gives us 3 multiplied by 32 minus 35, which equals to 3 times negative 3, which equals to negative 9. Okay, so now to calculate our determinant, we're going to put that all together. So we're going to grab this value, and this value, and add them up. So that means that our determinant for C equals to, what do we have? Negative 3 plus 12 minus 9. And this equals to 0. So since this equals to 0, that means that we have a singular matrix, just like how we saw in our previous examples. So then this means that the matrix is non-invertible. So we can see that these same properties hold whether it's 2 by 2, 3 by 3, or n by n. And we just have to break it down into all the different steps to figure out whether it's invertible or not by looking at whether its determinant is 0 or non-zero. So here we can see that it's not that challenging to take a determinant of a 3 by 3 matrix. We just have a few more steps we need to go through. I've showed you how you can derive this formula for the determinant, and you can also now take this formula and memorize it if that's what you prefer. So if you enjoyed this video today, please drop a like and comment any questions that you have, and please subscribe for more videos. There's going to be a lot more on linear algebra coming your way, and I'll see you next time.